this is a great time to get started with quantum computers. The train is sort of leaving the station. And if you don't know how to do small problems in quantum computers today, you may find it difficult to do truly useful business problems in a few years when quantum computers catch up.
Welcome to Embracing Digital Transformation, where we investigate effective change leveraging people, process, and technology. This is Darren Pulsford, Chief Solution Architect, author, and most importantly, your host. On this episode, Embracing Quantum Computing Basics with special guest and fellow podcaster Yuval Boger, Chief Commercial Officer at Quera Computing. Yuval, welcome to the show.
Thanks very much for having me, Darren.
Hey, we had an interesting conversation about quantum computers the other day, and I thought, you know what, my audience needs to learn about this new emerging technology. It's not to be feared, or is it to be feared? We'll discuss that today. But before we get started, Yuval, tell my audience a little bit about who you are and why we're talking to you today.
So my name is Yuval. I'm Chief Commercial Officer of Quera. Quera is a Boston-based company that makes quantum computers. Before Quera, I was Chief Marketing Officer of Classic, a software company for quantum computers. So I've been in quantum for a while. And in my career, I've been, for over about 20 years, CEO of various leading-edge companies, from virtual reality to enterprise software and many, many other topics. And it's always been at the forefront of technology, and that's why I'm so happy to be here. And when I'm not doing quantum, I'm an amateur violinist and enjoy playing with orchestras here and there.
That is awesome. I love music, as my audience knows. My kids all play a string instrument. Well, most of them all play a string instrument, either violin or cello. I just love the string instruments. So that's a great hobby to have. It's more than a hobby, though, isn't it? It's kind of a passion for most people.
It is kind of a passion. And when I was growing up, I studied physics. I have a master's in physics, and many, many years ago, I thought maybe I could be the best physicist out of the violinist, or the best violinist out of the physicist. And then it turns out that Einstein played violin and he was really good at it. So that dream went out the window.
That dream's out the window. Darn. So you got to pick up the cello or one of the obscure older instruments out there, like the cello da gamba or something like that.
Viola da gamba, right?
Yeah, exactly. So, all right, but also you have an unusual name. It's not a name I'm used to pronouncing. So, where are you originally from?
So I'm originally from Israel. Yuval is actually from the Bible, from Genesis. And believe it or not, in the Bible, it says that Yuval was the father of all the string instrument players.
Oh, there you go. That's awesome. Oh, that's wonderful. That's really cool. But hey, let's not talk. We can go on and on about string instruments. Let's talk about quantum computing. Because it's and you've already admitted this. You like to live on the bleeding edge of technology. You really do. You're way out there. But can you help explain to the layman like myself and people listening to the show what is quantum computing? It's not like we see with the superheroes like Ant-Man, like it's not going super small. What is really what does quantum computing do?
So a quantum computer is a special type of computer. It's based on the rules of quantum physics. And quantum computers, when they will be sufficiently developed, and we're still not there yet, should be able to solve problems that classical computers cannot or never will be able to. And these kind of problems could be anything from optimization problems, we can talk about some of those, a drug discovery, and many, many other applications. So it promises to be a new type of supercomputer, again, based on the principles of quantum physics.
Okay, so does it replace traditional computing completely? Or is it solving problems that traditional computers just can't solve? What's the difference?
we expect quantum computers to augment traditional computers, just like GPUs, graphical processing units, have not replaced CPUs. Just like
Right.
you're not running a Zoom call or doing Microsoft Word on a GPU, we don't expect you anytime to do that on a QPU, on a quantum processing unit. So quantum processors will be more of a co-processors that are good for very specialized calculations, but those specialized calculations they will be able to do faster, cheaper, with less energy, or be able to do them at all more than classical computers could.
Well, when you said at all, it reminded me of my computer science class on computational theory, right? And we talked about NP complete problems and the traveling salesman problem, right? Something humans could easily try and figure out 50 different locations. I can, on a map, I can draw the best route. Quantum, traditional computing, that is a brute for. It's really difficult to find that optimized path to take. Humans can do it pretty well, but quantum computers, this is where they shine. Is that correct?
Yes, and I think you brought up an excellent use case. So the traveling salesperson problem, sometimes we think about it in the context of a FedEx driver.
Yeah, there you
FedEx
go.
driver has 100 packages to deliver. What's the right sequence of deliveries? And not to mention that during the day, that answer, what's the right sequence, could change because maybe there's a traffic jam someplace, or maybe a customer has canceled the delivery. They don't need one anymore, or they want so. So this is not a static solution. It's something that could go on and change over time. So if you have only three packages to deliver, you and
That's
I can
easy.
do it in our heads. That's easy.
Yeah.
But if a quantum computer could do that almost in real time based on changing traffic conditions. And by the way, what's the best route? Is it the shortest route? Is it the route that takes the least amount of fuel? Is it the route that prioritizes certain customers? The, the question, what's the optimal route, could change as well. But imagine if FedEx had a quantum computer that could solve that. And all of a sudden, they were able to reduce their fuel consumption by, say, 15-20%.
That would
That
be
would give them an
huge.
unimaginable advantage over UPS or DHL or someone else. So this is one reason why companies are truly exploring the benefits of quantum computers for problems like traveling salesperson and other optimization problems.
All right, folks, a quick breather here. In my time of working with tech company founders, I come to one important realization. Certain tools can truly be a game changer. That's why I'm excited to talk to you about Nasuni, an enterprise data platform for hybrid cloud environments that powers business growth with effortless scalability, built-in security, and fast edge performance. Nasuni consolidates network storage and backup, eliminating data silos without changing your apps or workflows. Clients love the easy setup, rapid file sharing between offices, and the ability to leverage detailed analytics that matter. Data fluidity from the unique way data is stored increases its value, providing support for future AI initiatives. Plus, the centralized management model frees up your IT team to focus on more strategic business objectives. Head to nasuni.com/embrace to see how it can revolutionize your data infrastructure today. All right, now back to the show. Okay, so because I use Google Maps or Waze, depending on how I'm feeling, right? Isn't that already solving this problem? Doesn't that already exist?
Well, there's no doubt that you could use Google Maps to find a route that would go through 50 or 100 stops.
Right.
But what's the right order? I mean, even for Google Maps, you say, I want to start here and stop there and then go to this next stop, and then you find a route. But it doesn't tell you which one to
What the
do first and
optimal
which one
route
to do
is.
second.
You're right. I've done that when I've done deliveries with my wife. Around Christmas time when we're delivering things to our friends, and I put it all in the map. And she goes, "Why are you putting that in the map?" And it just does it in the order that I have. So I spend all the time pulling them apart and moving things around myself. So what you're saying is that quantum computer can do this like instantaneous. That's one of its big
We'll be
things.
able to do it. I mean, I think we have to be realistic about what quantum computers could do today and what they may be able to do in 3 or 5 or 10 years. But this is a great time to get started with quantum computers. You know, the train is sort of leaving the station. And if you don't know how to do small problems in quantum computers today, you may find it difficult to do truly useful business problems in a few years when quantum computers catch up.
So does this require a different way of programming? Are there a whole brand new types of programmers that have to um, be created? I mean, to program a quantum computer, is that different than the way I program another computer?
It is typically different, and it's different in a couple of ways. And we spoke about the GPUs earlier, how GPUs
Right.
augmented CPUs. Well, think about GPU programming and how it compares
Yeah.
with CPU programming. So GPU programming, yeah, you could run much of the same programs, but to really take advantage of the GPU, you want to you want to
Massively
fashion
parallelized. Yeah.
massively parallelize, or you want to fashion the program differently. And so also to take advantage of the quantum nature of quantum computers, all these things that your listeners may have heard about, superposition and entanglement and interference and so on, one needs to think about problems in a different way. And today, many quantum programming languages are akin to assembly language on a CPU. They're very, very
Oh,
low
no one
level.
wants to do that.
Who would
That's
want to do
awful.
that? And could you really write something very, very serious in assembly language? But more and more, we're seeing frameworks that try to abstract away that complexity and make it easier for people to program in quantum computers. Or maybe companies that say, well, we don't do the generic problem, but if you have an optimization problem and you can do specify it this way, we've written the quantum computer program that tries to solve it for you.
Okay, so there's some commonality to the paradigms that we're used to in traditional programming, but just like the GPU, it's going to be different. I know the algorithms are completely different in quantum computing compared to what we've learned in traditional von Neumann, computing stacks, right? So
Absolutely.
okay, so should we talk about qubits and entanglement and all that? All that. You're a physics guy. You're just loving this stuff, right? I mean, so let's talk first about some basic concepts. There's this concept in CPUs called I have bits and I have bytes. I have words. These are fundamental. I have a on and off switch. I'm either on or I'm off. That's my bit, right? It's different in quantum. We're going all the way down to it's different in quantum. They use a weird term called a qubit. Can you explain?
Sure. So a qubit is a quantum bit. Indeed, it is the fundamental unit of computation in quantum computers. And you can think about a qubit almost like a coin that's midway in the air. So you don't know for sure if it's heads or tails. And if it's a fair coin, then you know there's maybe a 50% probability that it will end up being heads if you sort of stop it, and 50% probability if you stop it at being tails. So a qubit has certain probabilities of being zero and certain probabilities of being one. And a lot of what quantum computing programs do is they influence the qubits to change that probabilities over time and reach the solution. So let me give you a really simple example, if I may.
Yes, please, because I'm still confused.
Let's assume that you had let's assume that you have an optimization problem, and the optimization problem is you have three, say, locations to put cellular towers, and you're trying to decide if you're putting towers in all or one or which ones to do. So you have three
Okay.
stations, and in each one you can either put or not put a cell tower. So overall, you've got two times two times two, you've got eight results,
A results, right.
eight possible results. So what you would do in a classical computer, and again, three stations and eight possibilities is something that we could probably even
Okay.
do manually. But
Right.
you basically run them sequentially. You say, okay, I'm going to run the 000. I'm not putting anything down. I'm going to do 001. I'm going to put a station at the first. I'm going to put 111. And you could go through sort of all the different permutations. In a quantum computer, each of these qubits could be 0 or 1 at some probability. So if you look at all three, take 3 qubits and look at all of them combined, there's some probability that they could be in 000. There's some probability that they could be in zero
You
zero
know what?
one,
Okay.
so on and so on. And what a quantum program could do, maybe you start them off in equal probabilities, right? There's a whatever 12.5% chance that you're going to land on each of these. And then what the quantum program does is modify these probabilities, perhaps to amplify solutions that are better and to de-amplify solutions that are worse. And then after a while, you basically what's called measure. You sort of stop the program and say, okay, now I'm going to look at what each qubit is, and then see what the solution is. What's really interesting about that is, let's assume that I wrote this amazing program and I started with equal probabilities for all 8 solutions, and I ended up with 95% probability of the right solution, and the other solutions were 5%. Now, if you measure that, if you look at them only once, well, you have a 95% probability of finding the right solution. But if you look at it only once, you still have a 5%
5%
probability of
chance of
finding the
bad. Yeah.
incorrect solution. So sometimes, so what you do in many quantum computer programs, you run it again and again and again. And after a while, you sort of get a good enough sense, oh, this 95% seems to be the sort of the winning thing for me. So now, if we take it from 3 stations to, say, 50
16.
stations,
Oh, 50. Yeah, there you go.
now, if you want to run it on a brute force algorithm on a classical computers, you'd have to run 2 to the power of 50
That's a
um,
lot of numbers.
options. That would take you forever and then some. If you can run it on a quantum computers with 50 qubits, and these computers exist today, then if the program is written correctly, you have a decent chance of finding these solutions. And so the value of quantum computers, we will talk, I'm sure, about noise and coherence and errors and so on and so on. But as the number of qubits in a quantum computer becomes larger and larger, and as computers are capable of doing longer and longer calculations, meaning more sophisticated algorithms, then they're quickly approaching the point what sometimes people call quantum advantage or quantum supremacy, where a quantum computer could do things that a classical computer could maybe do in an infinite, in billions of years, so practically cannot do. And one of the other things that came out of perhaps of our discussion is every time you add a qubit, just 1 qubit, you double the number of options that quantum computer could explore, right? When we
Of
go to
course.
three
Yeah.
qubits to 4 qubits, from 4 to 5, from 50 to 51. So a quantum computer, the power grows exponentially with the number of qubits, whereas in a classical computer, it does not. And therefore, you can sort of imagine that there's going to be a point in time, perhaps in the not too distant future, where quantum computers surpass the capabilities of classical ones for certain types of
For
problems.
certain types of things, which are these big, huge problems with a lot of variables, right? I mean,
So
that's where they really fit well, right?
So that could be one. So I think people look today at 3 classes of problems that they're very optimistic that quantum computers will be able to help with. One is optimization. We talked about traveling
Right.
salesperson. We can talk about store placement. We can talk about cargo loading. Which technician goes to which customer service location, what cargo is loaded on what truck, and so on and so on. So there are numerous optimization problems. The second one is simulation. And when people talk about simulation, a lot of things that come up is chemical simulation, simulating the behavior of molecules. Molecules have atoms, atoms have electrons,
Right. Yeah.
atoms and electrons have interactions between them, and very, very quickly you get into a situation where a classical computer cannot effectively simulate the behavior of a molecule. So you start doing all these sort of, oh, I'll discount that and I'll discount that and I'll make
Right.
that
Yeah. You do
something.
shortcuts, right? Yeah.
And before you know it, you're sort of tossing the baby with the bathwater. You're not getting a good enough solution. And the reason chemicals could be so important is, imagine if one could develop better solar cells or lighter EV batteries or better vaccines or stronger plastics or what have you. So there is
Huge, huge
a whole
opportunity.
area in pharma and chemical that could benefit from that. And the last one is machine learning. Um, and people are seeing even today that quantum computers can help in machine learning, can generate scenarios that can train classical machine learning models, or sometimes run special quantum inspired or quantum machine learning algorithms that are yielding very interesting results. So it's not a universal solution to all the world's problems, but even if you did simulation optimization and machine learning, you could build
That's
a
a
very,
lot.
very valuable business.
Yeah, that's a lot. I know another area that people are worried about, and it's an optimization problem, is decryption, specifically breaking keys, right? Because the traditional keys that we have are prone to quantum computers, right?
Yes, I mean the
This is
today's
where the fear comes in, right? This is the fear part of this, right?
it does. I mean today's encryption algorithms mostly use two very large prime numbers. So if you and I each knew a very large prime number, say a 100-digit number, and we just published the product of that these two numbers, then it turns out that for classical computers to factor that, to take that multiplied number and see what it's made of, is very, very, takes a very, very long time. However, by now a very, very famous professor from MIT, Peter Shor, came up with what's known as Shor's algorithm that showed how a quantum computer could do that in reasonable time if the computer was sufficiently large and sufficiently capable. And that was sort of both if there's one event that sort of turbocharged the quantum computing industry,
That
it's
was
that,
it.
because everyone and their CIO brother said, oh, what's going to happen to my data? Every prime minister or president said, oh, so what if my adversary has this capability and I do not? And therefore, a lot of people started investing in national quantum programs, in learning quantum computers, in developing quantum computers, and so on. And of course, like any new technology, any revolutionary technology, there are good uses and bad uses,
And
right?
bad
There
use.
are
Yeah,
amazing
that's right.
things you can do on the internet, but then there are some not so amazing things you can do with it. Planes could be used for good or for bad, and
Yep,
so on and
we've
so on.
seen that. Yeah.
And quantum is no exception.
Great insight, Yuval. If you want to hear more from Yuval and Darren on quantum computing, check out our next episode. Thank you for listening to Embracing Digital Transformation today. If you enjoyed our podcast, give it 5 stars on your favorite podcasting site or YouTube channel. You can find out more information about Embracing Digital Transformation at embracingdigital.org. Until next time, go out and embrace the digital revolution.